Hello everyone and very welcome. In this video, we will going to talk about kube-proxy modes, iptables, and ipvs, and we'll deep dive into how they actually work. So this video is all about Kubernetes service load balancing methods and options. And I actually wanted to do this for a long time, but I just got some time last week and I put this together and I hope you'll enjoy it. So on the agenda, we'll have a quick overview of Kubernetes PODs, services, and kube-proxy and their relationship. So basically framing up this video, what is this all about and why we care about this proxy mode at all. Then we do a quick intro into Linux iptables. So before jumping into how Kubernetes load balancing and kube-proxy works in iptables, what you have to understand actually what iptables are and how they work. So let's provide a quick intro if you are not familiar with iptables. Then we'll discuss kind of more in details how load balancing works in iptables mode. Then following that, we'll concentrate on ipvs. I'll do a quick intro into Linux ipvs load balancing system, which is part of the operating system. Then we talk about a demo, or do a demo, and then we set up an ipvs load balancer for VM hosted service. Kind of a quick demo of how ipvs works outside the Kubernetes environment. And then you can imagine how then Kubernetes will be taking advantage of this load balancer. Following that, we'll do a demo on how to configure Kubernetes to use ipvs when you're setting up a brand new Kubernetes cluster. And following that, we do another demo. And in this demo, if you already have a cluster and you want to switch from iptables into ipvs, how you can do that. Then we talk about some of the advantages of ipvs over iptables mode. And finally, we discuss situations where Kubernetes may fall back to iptables. So I hope you'll join me. First, let's take a look at the relationship between pods, Kubernetes services, and kube-proxy. So the first thing to note is that pods are ephemeral, which means that they could be deleted and recreated at any time for a number of reasons. Therefore, clients must not bind directly to pods, to their IP addresses. So we need something else to create an abstraction over the pods. And that's where kube-proxy creates the Kubernetes services. So a service is really a virtual IP. It has an IP address. So this is a permanent IP as long as the service exists, regardless of the pods being deleted and recreated. This is permanent. So clients can bind to this IP address. They can also bind to its name. So when the service is created, it creates a predictable name for that service. And the syntax is as follows. The service name, for instance, in this case is app1 dot, and then the name of the namespace, in this case default, .svc.cluster.local. So local.cluster.svc, these are permanent. All the services will have those combinations. And then the next thing that kube-proxy does, it actually works with the Linux kernel to set up a load balancer. And how it does, it depends on the mode or on the mode of that we select. Either uses iptables, that is a default behavior. We can change that. We can set it to ipvs. And that is the meat of this discussion, is how these modes are different and how the load balancer will be different as a result of our selection and when to use which. The client then can bind to the service and then call the service, and then the load balancer will pick one of these pods. And the algorithm to choose which pod really, again, depends on the mode. In IP table mode, we only have one option, and that is round robin. However, if we switch to ipvs, we have more options. So next we will look at what the IP tables is, kind of a general overview of what the IP tables are, and then how load balancer in that mode work. And then we switch the rest of our attention, the rest of this video on ipvs, how to set it up and how it works. When we talk about IP tables, really we are talking about the firewall systems in the Linux environment. So firewalls has different rules, and those rules are divided into different tables, and hence the name IP tables is where the name comes from. These tables deal with different rules depending on the situation. For instance, the filter table deals with the packets if they're allowed or disallowed to enter or exit the computer system. For instance, the NAT table or network address translation decides if the source or the destination of the packet needs to be changed. And you can think of this when a client calls a Kubernetes service, the IP address of the service will need to be changed into the IP address of one of the pods in the back listening. So NAT table will be responsible for that. And the way that firewalls interacts with the packets is through net filters. And net filters are hooks inside Linux that makes this interaction possible. The tables are further divided into what is known as chains. As chains basically decide at what point the rules should apply, for instance, input, output, or forward. And finally, the rules really decides if a packet is accepted, dropped, or rejected. Now let's take a look at various chains. The input, the rules in this chain control the packets when they're received by the server. The output, this chain controls the packets for outbound traffic. Forward, this set of rules controls the packets that are routed through the system. Pre-routing, this chain assigns packets as soon as the server receives them. And the post-routing, the rules in this chain allow making changes to the packets after they leave the output chain. Now let's take a quick look at each one of those tables in the IP tables. As mentioned, the filter table really is responsible to see if the packet are allowed or disallowed to enter or exit the system. The NAT table, again, as discussed, it decides if the destination or the source of the IP of the packet needs to be adjusted. The manual rules, this table is used to alter the IP headers of the packet in some various ways. For instance, we can adjust the time to leave. So each packet has a time to leave or to TTL, and that TTL can be adjusted through this table. It also places an internal kernel mark on the packet for further processing. If the packet needs to be further processed, then it is marked in this table. Finally, the raw table, we need to realize that the Linux firewall system is stateful. That is, it remembers the packets that the packet that passed through it before this packet, and that is important. For instance, think of the situation where it is used as a load balancer through the NAT table. When you call a service, the first time it calls probably, for instance, the pod number 1, but it needs to remember when it calls, then the second time the service is called, then the second pod needs to be called, not the first one, because the first one is already called. So that is the nature of the statefulness of the firewall. However, there are situations where connection tracking is not needed, and the raw table is used to exempt packets from a connection tracking system. Now that we learned a little bit about iptables and how they work, let's walk through an example and see what happens when we deploy a service and how the load balancing occurs, and we also peek inside the iptables and look at the rules, the chains. So let's say we have this YAML file, which is in 2 sections. The first section, the kind is deployment, so we are deploying pods here. And the second section is service, so we create a service for our pods up here. Now, this is very simple. We select a name for our pod. We also select a label. Then we label the pods. Then under containers, we specify the image, where the image is coming from. And under ports, we specify what port number they will be listening on, in this case 8080. Under services, again, we select the name for it. We also select what labels what labels we are matching, which is hello world, which it matches those are labels up here. And then under ports, the service will select port 80. So the service itself will be listening on port 80. However, it forwards the call to port 8080 because that's where our containers are listening on. And finally, we select because this is a node port service, we select the port number. Is optional. If we don't select one, it will automatically, Kubernetes will select a random node port for you. Okay, let's say now we go to the command line and execute this YAML. The request go to API server, kubelet to CRI. CRI downloads the container. Then CNI, or Container Network Interface, creates the networking for the pod and also sets up the vet. These comes in pair, and that establishes the connection between the pod and the server. It also sets the default route for the pod and also programs the route table and adds a route so the client or the host will be able to connect to the pod and vice versa. And because there are 2 pods, it does the same thing on the other server. It downloads the pod, sets up the networking, and now we have our pods set up. The next thing that it does, because we had a service also, we were also deploying a service, then it goes through the process of setting up the service. So it creates or saves the request to the server, to etcd, and then the control manager, endpoint control manager wakes up, and then at this point, our pods have IP addresses, so add those 2 pods that we just created, add them at the endpoints and the port number that will be listening on. And then calls into kube-proxy. Kube-proxy creates the cluster IP, and then also it programs the iptables, and it establishes load balancing for these 2 pods, and it does the same thing on the other server. Now we can actually go inside iptables and view what rules were created, and we can do that if we open a terminal and we can execute this command, sudo iptables -n. Let's go through that one by one. So iptables is a CLI that allows us to interact with iptables. -n means that give the IP addresses when we display information, and don't display the host name, actually display the IP addresses. -t is what table we are looking for inside the iptables system. And we are interested in NAT because that's our load balancing occurs inside that. And -L means list, and then followed by a chain. And we have a chain name called kube services. So kube services, the entry point for the service packet. Basically what it means that all the services that are created by Kubernetes will be under this. And then it that also includes subchains for each one of those entries called kube-service. And then that dispatches the packets to the next one, which is that chain here. So if we execute that, we'll see that now this is a subchain. So what does this subchain apply to? Any source. So the source could be anything. The destination is 10.101.886.1.73, which is the cluster IP. So any packet that is destined for this IP address and also for port 80, this will apply to. So what does it do? So Kube's SVC acts as a load balancer and distributes the packets equally. So if we now go ahead and run the same command, but now pass this chain, we'll see that we have 3 entries. We are interested in these 2. We'll see that this has a probability of 50%. So basically, these correspond to these 2 nodes. And the first one, the probability of selecting the first pod is 50%. That's what it says. And if it's not selected, then by default, it selects the next pod, which the probability will be then 100%. And then kube-SEP chain represents a service endpoint. It simply does the DNAT. So if we execute this now and now pass in this chain name, we'll see that now we have 2 entries. So, and basically this is where the DNAT occurs. So it says that in over here, when the request comes in and the service, the IP address is this, then we do a DNAT or destination NAT, and we change it to 172.168.209, which is this guy here, that 144. And then the first one, and then this one, the cube dash mark and dash mask. So this is the rule. So source is this, so which is applied, which indicates this, and then destination. So what happens here is it says if this pod, for some reason, service calls itself and comes through the chain, then make sure that we do the source NAT. So we change the source from 172.168.209 to 144 to the IP address of the server, the node itself. The reason for that is we don't want to circumvent the process. We want to go back through the process. Otherwise, if we don't do that, then it answers this locally, and then it kind of gets out of the process. So that's what it means. It wants to make sure if this calls itself, for some reason calls itself, then it goes through this chain, and then it goes back through the IP to the node itself. It goes back to and follow the process as it was set out in the beginning. And we can do the same thing for the second one. If we look at the chain here, we'll see that again, it does a DNAT. This time it does for 172.16.9.68, which is the first one. So this is how the load balancing occurs when we use IP tables. So this works well. This is the default behavior of Kubernetes, and is battle tested and everything. However, there are some situations that this may not work, and one of those situations, or the main situation, is when we have thousands of services, then IP tables will not be performing well. And there are a number of reasons for this. Is because for each service that we add, multitude of rules needs to be added. Look at this, all the rules that we created for simply saying if we call this virtual IP, then route the call either to this service or to this. But we have a lot of services, and actually we didn't look at all of them. There are some change, for instance, this guy here, which applies to the node port. So there are many, many rules that it just creates for simply load balancing a service. Again, this is not a big deal when you have medium number of services. Let's say below 1,000. If you go over 1,000, then performance may become a problem. The other problem is that when we go through these chains and look for stuff, these are not indexed. So we have to do actually a table scan. We'll go through that and do a sequential search. Again, if the number of services is low, because this is happening inside kernel, is very fast. However, if we go again beyond 1,000 mark, then the performance might be becoming apparent, start degrading. Also, incremental changes are not supported. If we want to make a slight change to this, we need to copy all the rules, make changes, and then save all the rules back again. And one of the more important one is, this is really a firewall system, as you can see. It was really never meant to be used as a load balancer, but over the years, the firewall has kind of merged or morphed into load balancing as well. So, and that is where we might be looking at, or you might be looking at ipvs as an option instead of iptables to instruct Kubernetes to use ipvs rather than iptables. And this is what we are going to look at. The remainder of the course will be looking at what ipvs is and how we create those. So let's see how ipvs works. So ipvs stands for IP Virtual Server. It implements transport layer load balancing, also known as L4 switch, inside the Linux kernel. So to remind ourselves, let's take a look at the OSI network model. And these are the layers and layer names. So layer 4 is the transport layer, and it uses UDP, TCP and UDP. So basically provides load balancing at this layer. Keep in mind that there are also load balancers such as Nginx that operate at layer 7. However, in terms of raw performance, this always beats this. So that's why it's being used by Kubernetes behind the scene. So basically what we do is we set up an ipvs on a host, and that acts as a load balancer, sits between the clients and the server, and the clients really don't know anything about the backend servers. They call into that virtual IP address that we set up on the ipvs, and then they can talk, and then requests are sent on their behalf to the backend servers. Also, the machine that is configured as load balancer is also known as a director. So if you're reading the documentation and they talk about director, they're really talking about the load balancer. For routing, that is moving packets between the client and destination servers. Either we can configure it to use as NAT or network address translation. That is rewriting the IP addresses, or if all the clients and the servers are on the physical network, it can use direct, which rewrites the MAC addresses rather than IP addresses, which is faster. Or it can also use encapsulation in terms of using IP in IP and using a UDP tunnel between them. So let's take a look at how this actually works. So as mentioned, we have clients that there's the director or the load balancer sits between the client and the servers. So the first thing that we need to do is we need to define a virtual IP and port number, either TCP or UDP, that client can bind to. We need to also specify what kind of scheduling algorithm we use. Round robin is the most popular one, but may not always be the best option. So this is another advantage of using ipvs, is we have option here. If you use iptables, you're only stuck with round robin. But there are other options such as least connection, destination hashing, source hashing, shortest expected delay, and never queue. So these are other options that can be used. So let's see what happens when the client calls into this virtual IP address. So as part of the request, it sends its IP, source IP, which is the IP address of the client itself, and the destination would be the IP address and the port number of this server or this virtual IP. So when the request comes here, the director or the load balancer intercepts the call and changes the source for the source IP address of the client to itself, and the destination is changed to one of these servers according to which algorithms that being used. One of them is selected, and then also the port number. These are listening on port 8080. It also changes the port from 80 to 8080. And then when the request, when one of these responds, the result is sent back from the server, one of the servers, with the IP address of the server to the IP address of the director here. And then the load balancer then rewrites the IP address, and the source becomes this source because the client called this IP. So, sorry, this IP, and expects a response coming from the same source. Otherwise, the packets will be dropped. So that would be the source, and the destination would be the client itself. So this is very overview of how ipvs works. Now we are going to actually implement this diagram here and see how that works. Again, this is for giving you some idea of how Kubernetes uses this load balancing behind the scene. So in this demo, we're going to set up an ipvs-based load balancer. So we need a director, and this is the director that I've already logged into. So this server will be acting as our load balancer or a director. And line 5, we need to install a software called ipvs ADM, which is used to set up, maintain, or inspect the virtual server table in the Linux environment. I've already installed that, so I'm not going through the installation process. Then on line 8 and 9, we are going to, these are the two servers that we call real server, or these are the servers that will be behind the load balancer. So this is the IP address of one and port number. So these two servers both listen on port 8080. So if we run that right now outside of load balancer, this is the result that we get. A very simple service basically returns the operating system and type, and also the IP address of the host. The same thing with this. And these are current running. This is one server and this is one server. So these are two virtual servers that we will be using. So again, keep in mind, we are not dealing with Kubernetes here at all. I'm just showing you raw how these can be set up on a virtual server and how Kubernetes actually takes advantage of this. So in terms of Kubernetes, imagine that these two are two pods that are hosting a service. And then on line 13, we need to set up a load balancer, sudo ipvs ADM -a-t. So -a means add a service, -t, this is a TCP service rather than a UDP service. And this is the IP address of the director or the load balancer. And this is the host that, or the port number that we'll be listing out. So in essence, we are setting up a virtual IP address that client can call. And -s means the scheduler algorithm, and RR means round robin. So you're setting up a load balancer, which will be using round robin algorithm. And this is the virtual IP address and port number that can be used by clients. And then on line 17 and 18, we are adding these two servers to be behind this load balancer. So the command is ipvs ADM -a-t. Minus A, again, in this case means add a virtual service, minus, and then this is the IP address of the load balancer is set up here. And then this R minus R means real server. So this is the IP address of one of our server, a virtual server, and this is the port number. So these two will be listening on port 8080. And minus M means masquerade, which means that they are using NAT. So let's go ahead and execute that first. And then this. And finally this. So we have our load balancer set up. We can verify that on line 22. Sudo ipvs adm minus capital L means list the virtual server table. And as you can see now, we have these two servers now listening for traffic, and the forward method is masquerade, so it's going to use the NAT table. The load balancer server will be using NAT to forward messages or traffic to these two servers. Okay, let's go ahead and now test our load balancer. So curl http minus 192.168.0.14-80. So that is the IP address of our VIP that we set up, virtual IP address, and let's call that. And you'll see that it responds one of the servers, and the first one would be 89. And then if we call that again, this time will be responded by 13. Now that, so not the load balancer has been established. We can also look at more information, connection on line 27, sudo ipvs adm minus lcn. So L means list, and C connection table, and N numeric numbers. That is show IP addresses, not the DNS name. So let's go ahead and run that. And we'll see that, remember that we make two calls to our virtual or load balancer, and those are listed here. So first of all, the protocol is TCP. So expire when will, if the server doesn't hear, if the load balancer doesn't hear from these clients within this allocated time, we will drop those packets. And then these are the source IP. So I'm calling it from the load balancer itself. And then, and this is a virtual server, which is itself again. And these are the destination. So this is a quick demo to see how IPVCM works, and you can imagine how Kubernetes will take advantage of this. So think of this virtual IP address as a Kubernetes service, and think of this as Kubernetes pods that are behind that service. Now that we saw IPVS in action, let's go ahead and talk about how we can configure Kubernetes to use IPVS instead of iptables for load balancing. There are two methods. The first method is to configure Kubernetes during the installation process, or you can wait until the Kubernetes cluster is set up and then configure that later on. So I'm going to show you both ways. First I'm going to show you how to do it during the installation. So I'm going through the installation process. And this needs to be run on all nodes, both master and worker nodes. Basically, we're setting up the requirements. On line 12 and 13, it's a best practice to make sure that your Linux system is up to date. And then we need to install ipvs adm. That is a requirement that we need to set up before we initialize the cluster. So that's on line 16. Then on line 19, you need to set up a CRI, container runtime interface. I'm going to use containerd, but you could use CIRO or even Docker, although Docker will be going away. So probably if you're setting up a brand new cluster, I wouldn't recommend using Docker anymore. And then on line 22 to 25, this is how we set up containerd. We will need to make a directory, create a directory under etc called containerd. And then we run this command as su or administrator, containerd config default and the location of this file. So basically that file will be created and configured when it configures, installs the containerd and configures it. Then before installing Kubernetes, we need to get the key from Google, and that is on line 28. And then on line 31, we need to add Kubernetes to our cluster, to our repository. So that's on line 31. Then we install kubeadm, which is used for initializing the cluster, kubelet and kubectl. So those needs to be installed. Then on line 37, we need to edit this file, which is sysctl under etc folder. And we need to add this line to it. Basically, it allows an iptable on the node to correctly see bridge traffic. So even though we'll be, after configuring ipvs, it will, for the most situation, we'll be using ipvs for load balancing, but there are some situations that it fallbacks and it has some dependency on container, on the table, iptables, and I'll talk about that a little bit later, but make sure that you do that. And then on line 42, we need to add one to this file under /proc system sys inet ipv4 and ip_forward. Basically what it does is allow when the packets arrive at the node's network interface to be forwarded to pod. So, and ipvs actually depends on this. So you need to make sure you do this. Then we restart system. And then on line 49 and 50, we load a couple of modules, overlay and br_netfilter. So we need to load those two. And then on line 53, we need to modify this file, fstab, which is under /etc, and we need to comment out this line here. And this is for swapping because Kubernetes does not support swapping, so we need to disable that. And on line 57, we need to do disable swapping from command line as well. Then on line 60, we need to download all the images that are required by Kubernetes. So that's done. Then on line 64, so before initializing, next step is to initialize our cluster, and this to be run only on master. So make sure you only run this on your master. But before running the command, we need to get the create basically a configuration file. So we need to, let's go through the command kubeadm config print, and then init-defaults, and then we put it into a file called kubeadm. So we need to modify this. So these are default setup that kubeadm uses. We need to modify that, and I have the file here, and I'll provide that so you can use it if you like. So I've commented out the section that we don't need, and then under node registration, this is an important part. If you are not using Docker, then you need to specify which CIR you're using. In my case, I'm using containerd, so this is the location that will be, Kubernetes will be looking during, or kubeadm will be using during the installation, because that will set the default CRI to this. If you're using CIRO, so this is the location for it. If you're using a Docker, so this is the Docker location. If you're using Docker, you won't need to specify this because it assumes that by default, up to this point, actually, up to this version, kubeadm assumes that you're using Docker. If you are not, then you have to specify the CRI socket, and then you specify where the socket is. And then just leave the API server part as is. And then at the bottom, this is the most important part of we need to add this section to the configuration. And so start from here. So the API version, kube-proxy.config, ks.io/v1 alpha1, so that's the version, and the kind is kube-proxy configuration, and the mode is ipvs. So this is the kind of the key here. We need to make sure that you set it to ipvs. So let's go ahead, and then we can then run after you configure, after you modify that, then you run kubeadm init, and then --config, and the name of a configuration file that you just created. So let's go ahead and run that. It will take a minute or so to set up the cluster. I'll just wait. Okay, that's done. And this line is important here. If you are going to set up worker nodes, then you need to copy this and run it later on. I'll show you where. Okay. So that's done. Then we need to make on line 69, we create a folder, a hidden folder called kube under the home directory. So let's go ahead and do that. And then we copy. The reason for this is Kubernetes, when it sets up the cluster initially, it uses some certificates as the proof of authentication, and only it can access Kubernetes. So in order for us to be able to also access, we need to copy everything from this folder and put it in the folder that we just created. So let's go ahead and do that. And then we need to give access to that on line 71. Then on line 74, we need to, at this point, we need to set up a CNI. We needed, because the CNI is required, I'm using Calico, so I'm going to download Calico. One caution here, if Calico works with ipvs, if you're using a different CNI, just make sure, read the documentation and make sure it works with ipvs before doing that. So let's go ahead and download that. And then on line 76, you're going to apply kubectl apply -f, and then the Calico YAML file that we just downloaded that, and then it will go ahead and set up Calico as our CNI or container network interface. And then at this point, before doing that, if you are setting up additional nodes, first of all, you need to run this command, the command that you saw here. You need to copy and paste that and run that on each node. After installing your the requirements, the prerequisite that I showed you at the beginning, and then you need to run this so to join those servers as part of your cluster. So let's go ahead and clear those. Also, if you want to be able to run kubectl on those nodes, you need to copy this file that you created here. You need to also copy that to those nodes, so you'll be able to run kubectl from those as well. Okay, on line 82, now we can verify that our cluster is up and running. And yes, we can see this is the information. This is the master, and that is the port number that it's running on. And on line 85, I'm going to only set up one server, and that is master. By default, when you schedule deployment, they are not scheduled on master. So we need to untaint master, basically to allow it to be able to scheduler, be able to deploy pods to that, and that is on line 85. kubectl taint node. This is a node name, node-role.kubernetes.iso/master, and then -1. Okay, so that is now untainted. Now we can deploy application to it. So just to verify, on line 88, kubectl get nodes -o wide. So I only have one, and that is the master. So if you have more than nodes, then those nodes will be shown here. And now at this point, we'll check to see line 91 sudo ipvs adm -l and see what's going on. And we'll see that already Kubernetes added some services that it uses. They are already part of this. So it's a good sign that it's using ipvs. Now for verifying that, let's go ahead and deploy an application on line 94, kubectl create deployment hello world --image. So this is the image that we are going to deploy, which is basically a hello world application. Let's go ahead and deploy that. And to verify that on line 97, kubectl get deployments, and we'll see that hello world has been created. Okay. Now we are going to create a service on line 99. So to be able to access the service, the application. So kubectl expose deployment hello world --port 8090 --target port 8080. So the service itself inside container will be listening on port 8080. However, the Kubernetes service will be running on 8090. So the call will be forwarded from port 8090 from the server to the containers on port 8080. So let's go ahead and run that. So that's done. Now to verify, kubectl get services, and we'll see that this is our hello world, and this is port 8090 that we specify. And on line 103, we can also get the pods. So kubectl get pods -o wide. And this is the IP address of our pod. So it ends with 196. So let's go ahead and run ipvs adm to see if our service shows up now. And as you can see, 8090, this is the service we just deployed. So that is the service port 8090, and this is the IP address of the pod. So very much like the demo that we did previously with virtual services, with virtual servers, now we see that containers also, or pods will be also part of our load balancers. Okay, so let's go ahead and now we deployed it with one container. Now let's go ahead and scale it up to 4. So on line 108, kubectl scale -- replicas equal to 4, and the deployment name, which was hello world. Let's go ahead and do that. And now let's go ahead and take a look at ipvs adm again. And now we'll see that under 89, this service, which is listing on port 8090, we'll see that there are 4 pods. So ipvs, as we create services, it manages the load balancing for us, and those are added automatically to our load balancer. If you prefer to set the kube-proxy mode to ipvs after you set up your cluster. That is also possible. And I outline the steps here. So starting on line 11, we need to edit a config map called kube-proxy. So on line 11, kubectl, edit, config map, kube-proxy -n kube system. So this config map called kube-proxy in the kube system, we need to edit that. And then we need to scroll down to the IPS section and the mode here. Since we just set up this cluster, it's already set to ipvs. But if it's not set to ipvs, it will be blank. So you need to edit that. You need then to change to set the mode to ipvs. Just change from blank to ipvs. Also, we can change the scheduler mode. So these are the various modes, round robin, list connection, and so on. So if it's not set, in this case, which is blank, so it means it's round robin. So this is the default behavior. But if you like, you can change your situation dictates. You can set to one of these. So again, I'll provide the script. So if you like, you can set it up. So, and then we are not done yet. So I'm not going to make any changes here. So just quit. Once you do that, once you make the change here, then there's another step that you need to take. We need to actually delete the kube-proxy. So on line 14, we are going to capture the kube-proxy, and this is the command kubectl get pods -n no heads -n kube system. And then what we're looking for is a kube-proxy. So this is the trick to get the name of the kube-proxy. And then we can let's just do it, go ahead and do that. And then we can print the name. So this is basically the name of the kube-proxy. And then you need to delete that. So it's very important on line 16, delete this kube-proxy because the changes that you made up here when you edited the config map will not take place until you delete the kube-proxy and it creates a new kube-proxy. And at that moment on, then you will see the result and you will see that ipvs is set. And one way to check that on line 19, we can get again, the proxy name. And at on line 21, we can do a log, basically read the logs from the new kube-proxy that was just created. So once you delete the kube-proxy, one will be generated, and then you're looking for this using ipvs proxy here, and that is the clue that now the system has switched to ipvs. You can also then do the same command that we did before for another perspective of proof that the change has happened, and that's on line 25, sudo ipvs adm -l. So this is, again, for the situation that you already have a cluster and you want to switch to ipvs. Just be very, very careful with this because switching to ipvs, make sure that one of the most important things to check again is to ensure that the CNI provided that you're using is compatible with it. Let's summarize some advantages of ipvs over iptables. The first one is performance. As we saw, iptables doesn't use any indexes, so you have to do a complete scan of tables when you're looking for something, versus ipvs that uses hash table, which is very fast. It's like comparing having two tables, one doesn't have an index and the other one has in a database kind of scenario. And obviously the one that has indexes is usually a lot faster. The second one is in iptables mode, latency to add rule increases significantly. It's almost exponentially, as we will see, when the number of services increases. On the other hand, in ipvs mode, latency to add WIP and backend IPs do not increase when the number of services increases. And this is a comparison that the Kubernetes team actually published. And let's go through that together. So we have the number of services, number of rules, and then we compare how long it will take those, kind of do a little bit of apple-to-apple comparison. And so we'll have, in the scenario where there's only one, number of services is 1, and number of rules are 8. The performance is pretty comparable because they're very small. However, when we get to like 5,000 rules and 5,000 services and 40,000 rules, it took 11 minutes for iptables and only 2 milliseconds. So as you can see, the time for ipvs is flat, again, because it uses index tables, uses hash tables, and they're all indexed. And then if you go even further, we have 20,000 services and 160,000 rules. It took 5 hours for iptables, and again, only 2 milliseconds for us. So you see the time doesn't change for ipvs. So these are very significant differences. And as we discussed earlier, load balancing options, we are only, the iptables only supports round robin, but in addition to round robin, ipvs supports list connection, destination hashing, source hashing, shorter expected delay, and never queue. So in situations where you have to use a different load balancing algorithm, then obviously ipvs is the way to go. It supports server health checks and connection retries, which we don't get if we use iptables. And finally, supports sticky sessions. So the last topic I wanted to discuss before ending this video is when ipvs falls back to iptables. And it's not as bad as you might think, and we will see why. So ipvs will employ iptables in doing packet filtering, SNAT or masquerade. Specifically, ipvs proxier will use ipset to store source or destination address of traffic that needs drop or masquerade to make sure the number of iptables rules be constant no matter how many services we have. So it will use something called ipset to keep track of the source or destination traffic that needs to be dropped or masquerade. So what is ipset? So ipset is an extension to iptables that allows us to create firewall rules that match entire sets of addresses at once. Unlike normal iptables chains, which are stored and traversed linearly, ipsets are stored in indexed data structures. So basically, these are indexed tables, which are a lot faster, much faster than iptables. So you don't really get the hit that you would get if you were using primarily iptables. So what are some of those situations that ipvs will fall back to iptables? Really, all of them really deals with situations where you want to provide external access to your services in the Kubernetes environment. And you might be familiar with node port and load balancer, but there are other ways that you can do that through either setting, when you start the proxy, kube-proxy, you pass in the masquerade all, and then provide the routes from outside into your Kubernetes. So that's one way of doing that. And then the other way is to create external services, which you provide the IP addresses that then kind of bypassing the whole Kubernetes and provide ingress access into Kubernetes. So there's not much time to discuss some of those situations here, but you can look them up if you're interested, or if you want me to cover in the future demo, just let me know in the discussion section. So I hope that you enjoyed this, and I hope it was useful. If you have any questions or comments or suggestions for future videos, please don't hesitate to let me know and post your comments and questions. I read them all and reply to all of them. Thank you and have a great day.